Hello, everybody. We're continuing in section 2.4, and now we're up to theorem 2.14, 2.14. And this is a property of invertible matrices. A square matrix is invertible if and only if it can be written as a product of elementary matrices. Now, we've actually established a lot of what we need to prove this, so the proof should be relatively not so bad. But I want to just clarify if and only if. I think this is the first time we've seen this phrase in this class, I think, although I don't remember. But it means that if A is invertible, then it can be written as a product of elementary matrices. And if A can be written as a product of elementary matrices, then it is invertible. So we really have to, so this is kind of like, in a way, it's like two proofs in the price of one. It's like two theorems in the price of one, so to speak. And to prove this, we kind of have to prove it in like both directions. We're going to have to prove that if it's invertible, then it could be a product. And then we're going to have to separately prove that if it's a product, it's invertible. But that won't be that hard. So let's start with the first direction. We're going to assume that A is an invertible matrix. Now here we're going to follow along here. So we're going to assume A is invertible. And from theorem 2.11, now what is theorem 2.11? Funny you should ask. I have it right here. Theorem 2.11 says that if A is an invertible matrix, then the system of linear equations AX equals B has a unique solution given by X equals A inverse B. And this is something we've established and proved and demonstrated and done already. This is in section 2.3. Okay, so we know that that no matter what B is, there's going to be a unique solution. So let B equal to 0, that column matrix. So now we have, if we make it a set of linear equations of the form AX. Now, X here is not one letter. X is a column of variables. And this has only one solution based on theorem 2.11. That's what 2.11 was saying. But what is that one solution? Well, the one solution has to be the trivial solution, which is all zeros. Because if I have a set of homogeneous linear equations where like 3x plus 2y equals 0, 5x plus 9y equals 0, well, obviously if x is 0 and y is 0, that's going to work out. So that's true whether it's 2 variables or 3 variables or 27 variables and 27 equations. Anyway, this implies that the augmented matrix, if I would take matrix A and augment it by putting the 0 matrix next to it, I can go do all the elementary row operations, all the switching and moving around to get it to look like I0. Now, now the A turned into an I, but the 0 stays a 0 because when I move the rows around, I add rows and multiply rows and switch rows. Well, the rows on the right side here are all just zeros. Get it? The rows are Z rows. Get it? But what did I do? I did all my elementary row operations. And that's how I got the A to look like the I. Now, we learned already, that's what we've been learning in this section, is that the elementary row operations correspond to the elementary matrices, E1, E2. So whatever I did first, that's E1. Whatever I did second, that's E2. Whatever I did next, that's E3. Up until EK, whatever K is whatever number of steps I had to do to get A to look like I. So if I start with matrix A and multiply that by E1, that's the same thing as doing the first operation. Then I multiply that by E2, that's the same thing as doing the second operation, whatever it is I had to do. And then I keep on going until finally, when I multiply by EK, A, the original matrix A, winds up looking like the identity matrix, with all just the ones down the column and the rest all zeros. So now it follows that A is equal to E. Now, if I start with this equation right here, so this little equation right there, and I don't like that, and multiply by EK inverse on the left, and the next thing on the left, dot, 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 dot. and then E3 inverse on the left, then E2 inverse on the left, then E1 inverse on the left, which is basically this guy right here. I'm going to be left with A. I'm just going to be left with that single solitary A. And on the other side, I'm going to have all these inverse matrices, really times the identity matrix, but you don't have to bother writing the identity because when I, so, but what I've done here, A is now equal to the product of elementary matrices, because we already showed just in the previous video that the inverse of an elementary matrix is an elementary matrix. So let's continue now. So that's the proof in one direction. So we've shown that if A is invertible, it could be written as a product of elementary matrices. Well, the truth is that's actually the hard part of the proof. Then the other part is really very easy. It's easy peasy lemon squeezy. So to prove the other direction, let's assume that A is the product of elementary matrices, which is the other direction of the proof. Well, since every elementary matrix is invertible, which is something we've established already, and the product of invertible matrices is invertible. Wait, who said that? Where do we get that from? Well, that was theorem 2.9, that if A, and this is something that, again, that we learned previously, that if A and B are invertible matrices, then the product AB is invertible, and the inverse of the product AB is B inverse A inverse. So this is something we've already established, just reminding you. Not for nothing. And so therefore, A is invertible, and that completes the proof. Now, let's I want to illustrate this a little bit. So let's go to this next example, example 4. Okay, so we want to find a sequence of elementary matrices. Let's just look at the problem here. We want to find a sequence of elementary matrices whose product is the non-singular matrix A. And A is -1, -2, 3, 8. Non-singular, just to remind you, non-singular means yes, it's invertible. So it's funny. Singular is bad, it's not invertible. Non-singular is good, it is invertible. Well, if you could, whatever you consider good and whatever you consider bad. Different people have different definitions of what's good and what's bad. Anyway, see how philosophical I got. Anyway, let's prove this. Let's do this. So we want to find a bunch of elementary matrices that multiply out to give us A. So what we're going to do is we're going to take this matrix A, and we're going to do all these different various row operations on it. So first, I'm going to multiply the top column by -1, and that'll be my new top column. So, and that's going to give me 1, 2, 3, 8. So my first thing I did is I did -1 times R1 became the new R1, but that's the same thing. That's the same thing as this matrix E1. Notice that E1, I multiply the top row. The top row is negative of what the original the identity matrix was. Don't forget what these elementary matrices, they're kind of starting. The starting point is always the identity matrix. Okay, next, going back to the matrix here, you have to buy. There's a lot of back and forth here. Going back to the matrix over here, we want to get rid of that 3. So we add -3 times the first row to the second row, and that gives us this guy right here. That's what we just did over. Oh, sorry, that's what we did over here, and that corresponds to this guy right here, 1, 0, -3, 1. Because to get from the identity matrix to E2, I added -3 times the first matrix, added onto the first row, added onto the second row. Okay, the next thing I want to do is I like to turn this 2 into a 1. So I'm going to multiply I'm going to multiply the second row by 1/2. And that's going to give me this guy right here. But the matrix that corresponds to this row operation is E3, 1, 0, 0, 1/2. And finally, what I need to do is I need to get rid of that 2 over there. So I'm going to subtract -2 of the first row of the second row from the first row, and that'll become my new first row. And so we're going to take row 1 plus -2 times row 2. That's going to become the new row 1, which is going to get me here, which is identity, which is what I wanted. But the corresponding chihuahua for that is this guy right here, E4. Now we've started with matrix A. Let's just recap here. We started with the matrix A. We did the first operation, which is the same thing as multiplying by E1. We did the second operation, which is same thing as multiplying by E2, and then E3, E4. And all I got to do now is multiply by all these inverses, like I did before, and I get that A is equal to E1 inverse times E2 inverse times E3 inverse times E4 inverse. So A is now a product of elementary matrices. Let's just see what are these inverses. Funny you should ask. So the inverse of E1 is that I multiplied the first row by -1. So the inverse would be to divide the first row by -1. Well, of course, with -1, multiplying by -1 divided by -1 is the same thing. But this is my E1 inverse. Now my E2 added subtracted 3 of the top row. So my inverse is going to add 3 to the top row. My E3 was to multiply the second row by 1/2. So my inverse of that is to multiply it by 2, because you multiply by 1/2, then multiply by 2, it restores it back to the way it was. And my E4 was to add -2 of the second onto the first. So now I'm going to invert that. I'm going to like reverse that by adding +2 of the second onto the first, and that's my inverses. So if I multiply these 4 matrices together, I will get matrix A, my original matrix A. Now I'd like you all to do this for practice, and it doesn't matter which you multiply first. You have to keep what it means is keep the order, but when you multiply these 2 first and then multiply that, or multiply these 2 first and then multiply, because matrix multiplication is associative. So that's why just make sure, just keep the order of don't switch the order of matrices, but it doesn't matter which one, which you get my point. Anyway, now in section 2.3, we learned the process for finding the inverse of a non-singular matrix A. And we used Gauss-Jordan elimination, and we did this whole smack. And then we got that. We started with A, we did all these different operations, we got the identity. And then I can multiply by all the inverses, and I get, to I, and I get A inverse. So the sequence of elementary matrices that reduces A to the identity also reduces I to A inverse if applied, properly. So if you apply the corresponding sequence of elementary row operations to the matrix A and I simultaneously, you get, here's A, here's I, multiplied by all these different things here. So A, now, well, I'm multiplying, and it's almost like you're distributing. Like I'm multiplying everything, so it's like I'm multiplying by the A and then I'm multiplying by the I. It's kind of similar to distributing, because when I multiply these matrices times A, I get the identity. When I multiply these matrices times I get A inverse, which is what we've established up here. But if you think about it, it kind of makes sense, because when these particular matrices, these are elementary matrices. So what they do is they move the rows around. Well, once A and I are together, when I move the rows of A, it moves. When I move the right side of the left side of the row, it also moves the right side of the row. So it's all happening at once. And now, this finally justifies why this method works. This method, which I said, okay, we kind of justified it. This really proves why it works, because when you have an augmented matrix AI, what you're really doing is you're multiplying by all of these elementary row operations, which produce the IA. And it's kind of like it's being distributing. But like I say, these are all row operations. So whatever I do to the rows in the left side of this, I do the rows on the right side of this big augmented matrix. Okay, anyway, now we come to the paste resistance for now, which is something which ties all of this together. Oops, I don't want that yet. This theorem, this beautiful, phenomenal theorem, theorem 2.15, equivalent conditions. All of these conditions are equivalent. See, it's so important. I'm making it nice and big. all of these conditions are equivalent. That is the fact that if given that A is an n by n matrix, these following statements are equivalent. 1, A is invertible. 2, A times the AX equals B, which is a system of linear equations, has a unique solution for every n by 1 column matrix B, meaning that if I have the same coefficients here of my system of linear equations, no matter what constants you throw at me, I'm going to be able to get a unique solution, meaning one and only one solution, just by multiplying both sides by A inverse, like we did previously. AX equals 0 has only trivial solution. So 3 is kind of like to me, 3 is kind of like a special case of 2, but it's fine. And 4, A is row equivalent to the identity matrix. IN means the n by n identity matrix. And 5, A can be written as a product of elementary matrices. Now, what does it mean to say they're equivalent? It means that if you have a matrix, and I can show that any one of these is true, if any one of these 5 things is true, that means automatically all 5 things are true. And on the flip side, if I have a matrix, an n by n matrix A, if I have a matrix, and I can show that any one, and I know that any one of these things is false, then all 5 are going to be false. So if I know that A is not row equivalent to the identity matrix, then I know then it's not invertible, it doesn't have a unique solution, it doesn't have only the trivial, and it cannot be written, and so, as a product, so forth. So it's either all 5. So once I know one of these things, I know all 5. Or on the flip side, once I know one of these things is not true, doesn't hold, then I know all 5 don't hold. This is going to conclude this little video. We're not done with 2.4. The next video is something super important, really important in the quote real world. But I want to make that a separate video. So I'm going to stop this now. I'm going to stop the madness now, and we will see you in the next video.